Alright, looks like we are live. Okay, let me continue. Let's continue. Let me open the table of content first. Okay, we are on chapter 19, patching faster translation here. And we already take a look at this. We already take a look at this too. And now we are in section 19.3. Who handles the TLP miss? Let me open that. Okay. Right. I have to take a look at this. How to speed up address translation. Right. By using the translation look aside buffer. Basically something like this. If we have the translation in the translation look aside buffer, we can immediately access that without consulting to the page table, something like that. Similar to how gates work, but the interesting part is that what happens when the case out of date, like the translation has changed or something like that. I'm still not sure. Okay, use caching when possible, right? And then also there's this temporal locality and spatial locality. Temporal locality basically, what is it called? An instruction or data item that has been recently accessed. Okay. Basically, case the, what is it called? Case the instruction or data that recently accessed. Basically, we are saving the data or instruction that recently accessed and will likely be reaccessed soon in the future. That is the temporal locality. And then there's also the spatial locality, which is basically save a memory at address, at specific address. No. Basically access a memory at specific address that will likely soon access the memory. Saving the memory at the memory address near the access address. Maybe something like that. Spatial locality. So we are not only saving the current access memory, current access memory address, but also the memory address near those address. Maybe something like that. Okay. Yeah, if you want a fast case, it has to be small, as issues like the speed of light and other physical constraints become relevant. how to best use them to improve performance, right? Okay. Like any case, take the translation look aside buffer rely upon both spatial and temporal locality for success, which are program properties. If the program of interest exhibits such locality, and many programs do, the translation look aside buffer hit rate will likely be high. Alright. Let me read this one. Who handles the translation look aside buffer miss? Oh, there's also this figure 19.3. Translation look aside buffer control flow algorithm. I assume it is handled by the OS, by the operating system. Maybe. Okay, this one TLP hit. Oh. Okay, one question that we must answer. Who handles translation asset buffer miss or TLP miss? To answer are possible the hardware or the software, the operating system. In the olden days, the hardware had complex instruction set, sometimes called CISC for complex instruction set computer. Oh, okay. And the people who built the hardware didn't much trust those sneaky operating system people. Okay, sneaky, right? Thus, the hardware would handle the translation aside buffer miss entirely. Oh, okay. To do this, the hardware has to know exactly where the page table are located in memory via a page table base register. Oh, okay. Page table base register. Okay, so it looks like, where is it? Is it in here? I don't think so. Maybe it is in here, right? This one, PTBR. Oh, okay. Can PTA here stand for page table entry, and PTBR here stands for page table base register. Okay, I assume this is some kind of base address, something like that, and then we add the virtual page number divided by the page table entry size to get the page table entry address and then access this page table entry address. Maybe something like that. Okay, where is it? So it is a page table base register. Okay, use in line 11 in figure 19.1. Right, the previous it is one. I have been wondering what this means. Okay. Alright. Is Is it only for the hardware though? I'm not sure. The truth is the hardware has to know exactly where the page table are located in memory via a page table base register used in line 11 in figure 19.1, as well as their exact format. Okay, their exact format. On a miss, the hardware would mark the page table, find the correct page table entry, and extract the desired translation. On a miss, the hardware would mark the page table, find the correct page table entry, and extract the desired translation. Update the translation look-aside buffer with the translation and retry the instruction. Extract the desired translation, update the TLP with the translation and retry the instruction. Retry the instruction. So does that mean after we update the TLP with the translation, we will look at the TLP again? Is that it? An example of an older architecture that has hardware managed TLP or hardware managed translation look-aside buffer is the Intel x86 architecture, which use a fixed multi-level page table. See the next chapter for the tile. Okay. The current page table is pointed to by the CR3 register. The current page table is pointed to by the CR3 register. What is CR3 in here? We use a fixed multi-level page table. Oh, okay. So instead of linear page table, we use a multi-level page table. Alright. The current page table is pointed by the CR3 register. Okay, more modern architecture, for example, MIPS R10K or Sans Spark, I guess. Put RISC or reduced instruction set computer. Oh, so previously we have this one, CISC, which stands for complex instruction set computer, I assume. Complex instruction set computer. Complex instruction set computer. Something like this. And then we have, what is it called? RISC. Reduce instruction set computer. Okay. Put RISC or reduce instruction set computer. Okay, more modern architecture. have what is known as a software managed translation log asset buffer. On a TLB miss or translation log asset buffer miss, the hardware simply raise an exception. Line 11 in figure 19.3. Okay, this one 9.3, which pause the current instruction stream, raise the privilege level to kernel mode, and jumps to a trap handler. So we are context switching to the kernel mode. As you make case, this trap handler is code within the operating system that is written with the express purpose of handling TLB miss. Trap handler is code within the operating system that is written with the express purpose of handling translation log asset buffer miss. When run, the code will look up the translation in page table, use special privilege instruction to update the translation log asset buffer, and return from the trap. Run, the code will look up the translation in the page table, use special privilege instruction to update the translation log asset buffer, and return from the trap. Okay. At this point, the hardware retrieves the instruction. So that is why we retry the instruction. Okay. So the one retry the instruction is the hardware. I'm assuming okay, yeah, maybe the CPU retries the instruction that check the translation log asset buffer again. Maybe. I'm assuming this translation log asset buffer is some kind of storage, cache storage to save the translation, right? The translation address, and hardware in this case might mean the CPU, maybe something like that. Okay, so that way we trace the instruction. Let's discuss a couple of important details. First, the return from trap instruction need to be a little different than the return from trap we saw before when servicing a system call. The return from trap instruction need to be a little different than the return from trap we saw before when servicing a system call. Okay. Return from trap instruction. Okay. In the latter case, the return from trap should resume execution at the instruction after the trap into the operating system, just as a return from a procedure call returns to the instruction immediately following the call into the procedure. Right. Okay. We are resuming execution, right? Basically, what is it called? Execute the next instruction after using a system call, right? Okay, immediately following the call into the procedure. Okay, in the former case, when returning from a TLP mishandling trap, the hardware must resume execution at the instruction that caused the trap. Okay, so instead of execute the next instruction, we are re-execute, maybe that's the word, we are re-execute the instruction that caused the trap, re-executing the TLP miss instruction, the instruction that caused TLP miss, maybe that's the word. This retry to let the instruction run again, this time resulting in a TLP hit, the translation look aside buffer hit. Thus, depending on how a trap or exception was caused, the hardware must save a different program counter. I assume PC in here means program counter. The hardware must save a different program counter when trapping into the operating system in order to resume properly when the time to do so arrive. Okay. How a trap or exception was caused, the hardware must save a different program counter when trapping into the operating system. Oh, okay. In order to resume properly when the time to do so arrive. Okay. Second, when running the TLP mishandling code, the operating system need to be extra careful not to cause an infinite chain of translation look aside buffer miss to occur. Need to be extra careful not to cause an infinite chain of translation look aside buffer miss to occur. Many solutions exist. For example, you could keep translation look aside buffer miss handler in physical memory where they are unmapped and not subject to address translation, or reserve some entries in the translation look aside buffer for permanently valid translation and use some of those permanent translation slot for the handler code itself. This way translation always hit in the translation look aside buffer. Okay. Keep the TLP miss handler in physical memory. Oh, okay. Where they are unmapped and not subject to address translation, or reserve some entries in the TLP for permanently valid translation and use some of those permanent translation slot for the handler code itself. This word translation always hid in the translation look asset buffer. So we have a permanent translation slot. Okay, interesting. We can save the TLP miss handler in physical memory or in the translation look asset buffer itself. The permanent translation slot. Okay. Maybe when the operating system booting up, we actually using this permanent translation slot for some of the kernel memory. Yeah, maybe something like that, or the memory that the operating system will use. Maybe. Okay, I'm not sure if that is correct or not. The primary advantage of the software managed approach is flexibility. Okay. The operating system can use any data structure it wants to implement. The page table without necessitating hardware change. Another advantage is simplicity, as seen in the translation look asset buffer control flow and 11 in figure 19.3 in contrast to line 11 until 19 in figure 19.1. Okay, this one, right? Figure 19.3, and also, yeah, I think this one for figure 19.1. Oh, so this is the translation look asset buffer with the hardware, I assume. This algorithm. And the figure 19.3, this one is the translation look asset buffer when the operating system handle the what is it? The translation look asset buffer look up. Maybe something like that. Oh, wait. But yeah. Is this happening in the operating system or in the hardware? I'm assuming this is happening in the hardware, and then the operating system is the one gonna handle the exception here rather than the hardware. Maybe. The hardware doesn't do much on a miss, just raise an exception and let the operating system translation look asset buffer miss handler do the rest. Okay, it looks like in the figure 19.3, the translation look asset buffer control flow here is from the hardware side, and then when we cannot find the translation in the translation look asset buffer, which caused the TLP miss, then the operating system take control of that. Maybe something like that. Okay. Let me read the aside here first. I did read this one previously. Yeah, I'm just making sure that I didn't skip the aside. Okay. Aside RISC versus CISC. In the 1980s, a great battle took place in the computer architecture community. On one side was the CISC camp, which stood for Complex Instruction Set Computing. On the other side was RISC for Reduced Instruction Set Computing. The RISC side was spearheaded by David Patterson at Berkeley and John Hennessy at Stanford, who are also co-authors of some famous books. Okay. Although later John Cook was recognized with a Turing Award for his earliest work on RISC. CISC instruction set tend to have a lot of instruction in them. And each instruction is relatively powerful. Okay. And each instruction is relatively powerful. For example, you may see a string copy which takes the pointer and a length and copies byte from source to destination. Okay. You may see a string copy which takes the pointer and a length and copies byte from source to destination. The idea behind CISC was that instructions should be high-level primitive to make the assembly language itself easier to use and to make code more compact. The idea behind CISC was that instructions should be high-level primitive to make the assembly language itself easier to use and to make code more compact. Okay. RISC instruction set are exactly the opposite. A key observation behind RISC is that instruction set are really compiler target, and compilers really want are a few simple primitives that they can use to generate high performance code. Okay. Key observation behind RISC. Instruction set are really compiler target. And all compilers really want are a few simple primitives that they can use to generate high performance code. Thus, RISC proponents argue, let's rip out as much from the hardware as possible, especially the microcode, and make what's left simple, uniform, and fast. Okay. level primitive, maybe something like that. Or maybe, yeah, easy to use, and this one is okay. A few simple primitive. Simple instruction. Yeah, simple does not mean easy, alright. Usually easy to use is not simple because we need to provide a bunch of stuff to make it easier to use. Okay. In the early days, RISC chips made a huge impact as they were noticeably faster. Oh, okay. Many papers were written, a few companies were formed, for example, MIPS and Sun. However, as time progressed, CISC manufacturers such as Intel incorporate many RISC techniques into the core of their processor. For example, by adding early pipeline state that transform complex instruction into micro instruction, which could then be processed in a RISC-like manner. Oh, okay. Adding early pipeline states that transform complex instruction into micro instruction, which could then be processed in a RISC-like manner. Now I'm kind of curious, what is the cause of this transformation, from complex instruction into micro instruction? I mean, if the cost is small, then yeah, this might be good thing. But again, like like the paging concern here, if we split up too much, right, we might have some problem when searching to those pages, That's why we have the translation look aside buffer hardware, right? Yeah, I'm not sure if the translation look aside buffer is another, what is it called? Is another kind of processor, maybe something like that, or it is just a storage base. I mean, it is. If it is a case, then I assume it is a storage rather than processing unit, but who knows? I'm still not sure how to validate that, how to verify, I mean. Okay, which could then be processed in ISC-like manner. This innovation, plus a growing number of transistors on each chip, allowed CISC to remain competitive. The end result is that the bit died down and today both types of processor can be made to run fast. Okay. So even when the CISC have the transformation phase from the complex instruction into the micro instruction, it can still run fast. That is fascinating. How did they do that? I am curious. Okay, that is the first aside here. Both RISC and CISC. And then another aside. Take a look. Not take a look. Yeah, if I remember correctly, a lot of resource. What is it called? Say that TLB stands for take a look, aside buffer, something like that. But in this case, it is a translation look aside buffer. So I'm not sure which one is correct, or maybe I'm just misremembered that. Yeah. Hello, pornography. What you studying for? I'm studying for fun, I guess. I'm trying to learn how the operating system works by reading this book, Operating System 3 Easy Piece, and currently on chapter 19, learning about patching with the translation look aside buffer for faster translation from virtual address to the physical address, and currently on section 19.3, who handles the translation look aside buffer miss, something like that. And now I'm reading this aside. The translation look aside buffer valid bit not equal page table valid bit. Okay. I defend my IT engineering bachelor thesis today. Literally just graduate. Good on you, dude. Good on you. Keep going, dude. Oh, okay. Good luck for your thesis too. Oh, or maybe you are the defend your thesis. Anyway, good luck for your graduation, pornography. Okay. Wait, let me read this. The translation look aside buffer valid bit not equal page table valid bit. A common mistake is to confuse the valid bits found in a translation look aside buffer with those found in a page table. Okay. In a page table, when a page table entry or PTA is marked invalid, it means that the page has not been allocated by the process and should not be accessed by a correctly working program has not been allocated by the process. Okay, that is invalid, right? And should not be accessed by a correctly working program. The usual response when an invalid page is accessed is to trap to the operating system, which will respond by killing the process. Again, usual response, which means that there are unusual response too, right? Just something to keep in mind. So when the program crashes, well, that might be the usual response. A translation asset buffer valid bit, in contrast, simply refers to whether a translation asset buffer entry has a valid translation within it. Oh, okay. A valid translation within it. When a system puts, for example, a common initial state for its translation asset buffer entry is to be set to invalid. Okay. For each translation asset buffer entry is to be set to invalid because no address translation are yet cached there. Okay. Once virtual memory is enabled and once programs start running and accessing their virtual address space, the translation asset buffer is slowly populated, and thus valid entries soon fill the translation asset buffer. The translation asset buffer valid bit is quite useful when performing a context switch too, as we'll discuss further below. By setting a translation asset buffer entries to invalid, the system can ensure that the about to be run process does not accidentally use a virtual to physical translation from a previous process. Oh. So I'm assuming that when the previous process finishes, or maybe when the current process finishes and another process about to be run, the current or previous process translation will be marked invalid. Is that it? So that the lifetime of translation look aside buffer entries until the process finish. Is that it? I'm not sure. But yeah, this is something to keep in mind. TLP valid bit. Okay, bit. Refers to whether TLP entry has a valid translation within it. Yeah, maybe something like this. By default, default, the TLP entry is set to invalid. And then yeah, there is also page table valid bit, right? Which we take a look previously. Right, the page has not been allocated by the process. Something like that. Okay. It is different from page table valid bit. Okay. Alright. Yeah, that make me wonder about the lifetime of the TLP entries. What is the lifetime of entries? Until the what is it? Until the TLP entry become invalid. Okay, maybe something like this. Till the TLP entry become invalid. Okay, the TLP content. What is in there? Let's look at the content of the hardware. TLP in more detail. Okay, is it? Oh, is your replacement policy, right? Maybe we can get the answer in this section later on. Oh, context switches. Okay. TLP content. Yeah, let me read this. Guys, TLP contents. What's in there? Let's look at the content of the hardware translation look asset buffer in more detail. A typical translation look asset buffer might have 32, 64, or 128 entries and be what is called fully associative. Fully associative. Okay, what does it mean? Is fully associative means from TLP contains what's in their section. Basically, this just means that any given translation can be anywhere in the TLP, the translation look asset buffer. Oh, this just means that any given translation can be anywhere in the translation look asset buffer, and that the hardware will search the entire TLP in parallel to find the desired translation. Oh. Active in TLP means it looks like what is it? Any given translation can be anywhere. Maybe means that any given translation can be anywhere in the TLP, and the hardware will search the entire TLP in parallel to find the desired translation. Yeah, maybe something like that. TLP entry might look like this: virtual page number, page frame number, okay, author page, probability offset, maybe something like that, or maybe author page that is not the offset. Yeah, I'm not sure. Okay, note that both the virtual page number and page frame number are present in each entry, as a translation could end up in any of these locations. In hardware terms, the translation look aside buffer is known as a fully associative case. Oh, okay. Fully associative case. The hardware searches the entries in parallel to see if there is a match. More interesting are the other bits, right? For example, the translation look aside buffer commonly has a valid bit. Oh, okay. Right. Which says whether the entry has a valid translation or not. Also common are protection bit, like the permission bit, if I understand correctly, which determine how a page can be accessed. Right? Do we have any permission to access the page? As in page table, for example, code page might be marked read and execute, whereas heap page might be marked read and write. Read and write. Oh, okay. Read and execute the code page, whereas heap page might be marked as read and write. There may also be a few other fields, including an address space identifier, a DT bit, and so forth. See below for more information. Where is the information? Is this the one? Maybe. Okay, so the other bits might contain valid bit, and then protection bit, and then address space identifier, a DT bit, and yeah, another bit, I guess. Hello, I wrote okay. What is happening? I'm trying to learn about operating system by reading this book, Operating System 3 Easy Pace. You can take a look at the description for the resource. And currently I am on chapter 19, basically learning about patching mechanism for memory management with the translation aside buffer that can, that can make the translation faster, the translation between virtual address and physical address faster. Virtual address to physical address faster using the translation aside buffer or the case. And currently on section 19.4, the TLP contains what's in there. Okay. Oh, it's raining. Alright. Okay, maybe. Yeah, let's continue this section 19.5, TLP issue context switches, on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.